So the today's is actually the distribution of particles. Today's class is about distribution of particles into energy levels. Distribution of particles. This could sound very easy to you, but I have seen that even I have made a lot of mistakes in this topic, and every student does, because it is very confusing topic. So there are some rules which I want you to remember, and then we will solve some practical problems to implement those rules. Number one rule is, so in the question it will be told to you that this many energy levels are given. Okay. Now energy levels could be of anything. For example, harmonic oscillator energy levels, infinite potential well energy levels, or random energy levels, 3 energy levels, 4 energy levels. It can be mentioned here. And then they will mention the type of particles. So for each type of particles, there are some set of rules which needs to be obeyed. So type of particles is the number one thing. Okay. And then comes the rule. Okay. So that in types of particles, number one particles comes fermions. So when it is mentioned in the question, so I think before coming, okay, let's start with fermions. So if in the question it is mentioned that you have 6, 7, 8 fermions or any number of fermions, and you want to distribute into this many energy levels, then the rule which you need to obey is 1 fermion in 1 energy level. 1 fermion in 1 energy level. Why? Because the Pauli exclusive principle says that no two fermions can have the same quantum state. But there is one additional thing which comes under this. Sometimes in question it is not mentioned that it is fermions. It is mentioned that it is either electron or proton. So before coming to that, you must know what is fermion. Fermion is a particles with spin 1/2, 3/2, 5/2, so on. So every particle in quantum mechanics, even if you are BSc student, you can this much know from the knowledge of lower classes, then let that electron, proton, and these kind of things have the spin. All the quantum particles have some spin. We will not go in detail that what is that spin. If the particle have the spin like half, 3/2, 5/2, it means that that particle is a fermion. Okay. But if only in the question it is mentioned that the particle is a fermion, then you do not usually consider the spin part. Okay, then you put 1 fermion in 1 energy level, that's it. If it is clearly mentioned it is fermion. If it is mentioned that it is electron or proton, it means the particle has a spin half. You have a half spin particle, because electron and protons have half spin. In this situation, there will be 2 electrons or protons in each energy level. Or in general, if I say there are 2 s plus 1 in particles. So s is a spin. So if you put half here, you will get an answer 2. That is why 2. So why? So electron proton is a fermion, but then why we are not putting 1 for electron in 1 energy level only? The reason being, the Pauli said no two fermions should have the same quantum state. The moment we are talking about fermions, we are not considering one quantum number that is called ms quantum number, which you should not worry about right now. But it is one quantum number, ms quantum number. If s is half, then ms quantum number can take value plus minus half. A very simple thing from hydrogen atom, maybe sometimes in lower class you must have studied. Don't worry about it. So when we are only talking about fermion word, then we are not talking about ms. The moment you start talking about electron or proton, or you have specified the spin that you have 8 spin half particles, even at that moment you started to talk about this extra quantum number. It means you added an extra quantum number to your system. Now the same 2 electrons the same two electrons, electron 1 and electron 2, become different because to one electron you assigned half and to another electron you assigned minus half, because you introduce new quantum number which is called ms. So to overall conclusion for that is, if only fermion is mentioned, one fermion in one energy level, if electron proton is mentioned, you need to do two electrons or protons. So let's say I say spin 3/2 particle is there. How many particles you will put in each energy level? So anybody give me an answer. It's a very simple. You just need to put 2s plus 1 formula. Huh?
4.
4. 4 particles in each energy level. In each energy level. Similarly, any kind of fermion you can calculate. Okay. Only fermion, if said, one fermion in one level. If any particle like electron proton is mentioned or specifically spin is mentioned, you can use this by this formula 2s plus 1. Okay. So this is for fermions. Now comes the second branch of particles, which is actually called bosons. Bosons is a second class of particles, and these are particles which have integer spin, particles with integer spin. So can anybody give me an example of boson? Anybody know any example of boson? Boson particles. It's a very, very fundamental example. You are able to see because of this particle.
Higgs boson.
No.
Photons.
Photons. Higgs boson could also be a right answer. I don't know about that, but photon is one of the example. So if bosons are mentioned, bosons are the particles with integer spin, then you do not have to worry about spin at all. In any case, if boson is mentioned, you do not need to mention spin. Then put any number of particles in ground state energy level, or in any energy level. Okay, in any energy level. So you can put any number of particles into any energy level depending on question what has been asked. If they are asking what is a ground state energy, what is first state, depending on that you can manage. I will just explain with the question. Okay, so put any number of particles in any energy level. This is the only rule for boson. Third kind of particles is classical particles. If it is mentioned that the particles are classical particles, then also you can put any number of particles in any energy level. Put any number of particles in any energy level. Now the question also comes in one more way, that is indistinguishable particles and distinguishable particles. Now every quantum particle is indistinct, quantum statistical particle. So every fermion and boson, so let me write it here. If it is mentioned that it is indistinguishable particle, then it can either be a fermion or it can either be a boson. And if it is mentioned that it is distinguishable particle, then it is classical particle. Okay. Classical. What do you mean by indistinguishable and distinguishable? Let's say there are two particles, particle 1, particle 2. You say it is particle A, it is particle B. You can say this in classical particles that it is A, this is B. You cannot say in indistinguishable cases like fermions and bosons. Both are particles. I do not know which is A, which is B. Both are same. Both are A. Both are A. Okay, both are A. I cannot distinguish between them. Okay. Now there is one more confusion which comes, and this confusion has made a lot of disasters in the exams, and that is sometimes they say identical particles. Identical particles. So when the student reads identical particles, and usually these kind of questions are easy. After a while, you obtain a very good command on this kind of questions. So when a student in the exam reads identical particles, he or she gets happy, and he thinks it is indistinguishable particles. Identical word and indistinguishable words are two separate words, and you should not confuse them. In the question, sometimes in JEST also question have came, there are 5 identical classical particles. So now student is confused, either it is identical or it is classical. What is it? Because student is uh, confusing identical word with indistinguishable word. Identical simply means all the particles are either electrons or protons or of the same kind. Let's say there are two humans. We can separate two humans. It is human A, human B, but both of them are identical particles. That is, both of them are humans, but we can distinguish between two humans. So identical word is quite different from indistinguishable. So classical particles can also be identical, and in question they can mention that there are identical classical particles. Okay, they can say identical fermions, identical bosons. In this situation there will be no confusion, but if they say identical classical particles, there will be confusion. So never confuse identical word with indistinguishable. So with these rules, let's solve some problems, and after this you will never get confused. So problem number 1, question number 1. Okay, question number 1 is, so for a very simple case, we will assume that there are 4 particles. Okay, there are 4 particles and there are 4 energy levels, or we can say G, 4 energy levels. Okay, 4 energy levels. Now sometimes in energy levels, two kind of energy levels can be there. One is non-degenerate and one is generate. Okay, sorry, degenerate. So right now we assume that they are non-degenerate. What is non-degenerate, degenerate, that we will come later, but for now we are assuming they are non-degenerate particles, energy levels. So 4 energy levels. So let me draw 4 energy levels. So energies are also given. This has energy 0, this has energy 1, this has energy 2, this has energy 3. So let's say 1, 2, 3 electron volt. Units are electron volt. And now the first class of particles come, fermions. Fermions. Now the question to you can be asked in 2 ways. Number 1 kind of question is number of ways. In how many ways you can distribute these 4 fermions in these 4 energy levels? So the rule for fermion is one particle in one energy level. So if I put first fermion here, second fermion here, third fermion here, and fourth fermion here, I do not have any other extra option. I cannot put 2 fermions in one energy level. I have to do only this. This is the only one possibility which is there. So what is the number of ways? It is 1. So let's say there can be any number of ways, any number of particles. Then how do we solve it for that? So the general formula for that is NCG. NCG. What do you mean by NCG? N means 4C4. So 4C4 will give you answer. C means combination. 4C4 is so what is the answer of 4C4? It is 1. That is why here we got the 1. Now just to give make sure that this formula works right. Let's put one more energy level. So there are now 5 energy levels and 4 particles only. So now let's see how many ways we can do that. How many ways we can arrange. One more option is that we arrange like this. One more option is we arrange like this. Okay. Is there any other option? Yes. One more option is we arrange like this. So what is the total number now? 4 according to our diagram. And 4 or 5? I think there will be one more way. One more way will be there. Tell me which way is this?
second वाला खाली रहे.
हाँ, second वाला खाली रहे. Okay, perfect. So there are total 5 ways. And you can see if you draw in diagram there can always be confusion, but using the formula there is never confusion. 5C4 will always give you answer 5. So 5. Perfect. So for fermions our situation, our answer is right. Now there can be one more situation, one more kind of question that can come. What is the ground state energy of this system? If you put 5 energy levels, 4 particles in 4 energy levels, what is the ground state energy of the system? Most of the times when I ask ground state energy, students confuse it with the minimum energy our system has, which is 0. So student will tick 0, and trust me, in the option 0 will always be there. No, when they ask what is a ground state energy of system, it means they are asking when you distribute these particles in these energy levels, what is the minimum energy these particles will have? So that is you distribute all of them and now calculate the energy. So energy for this particle is 0 because it is in 0 energy level. Energy for this particle is 1, for this is 2. So if you add this 3 to 5 plus 6, so your energy for ground state is 6 electron volt. Okay. Now I again want to come to our case when there are 5 energy levels and still 4 particles. Now in this situation, if they ask what is a ground state energy, then you have to arrange your particles in such a way that the total energy which you are getting is minimum. And in which situation this will be minimum? When you arrange your 4 particles in first four states. Now they ask you what is the first excited state of this system. Then you do is you change the distribution and see that your energy is increased. Okay, your energy is increased. So how you will do that? So the very simple thing is you put this 1 to 4. Now your energy, so initially your energy was 6. Now your energy is, calculate 4, 3, 7 to 9, 9. Now there were very options to change this distribution. If I would have changed this by this, then what is the energy? 4 to 6 plus 1, 7. Okay. If I change it by taking it here, then my energy is 4, 3, 7 to 9 plus 1, 10. Okay. You understanding? So what is the ground state energy in this situation? Tell me. 4 particles in 5 states. 6. And how this comes? When we distribute in this way. Now tell me what is the first excited state? It is 7. Just put 3 to 4. Just put 3 to 4. If they asked, so ground energy 6, first state energy 7. Now comes to second state energy. How will that happen? So first bring it to ground, and now just put 2 to 4. Now you will see the energy is 8. So second is 8, second excited state, and the third excited state is first bring them to ground and then 1 2. So now the energy is 9, 4 3 7 2 9, and then if you do the last step, then the energy will become 10. Okay, so understand, everybody understood till here? If the energy levels are given and if the number of particles are given, how you find ground state, first excited state, second excited state energy for
Yes,
fermions?
yeah.
Yes. So for fermions, if it is clear, now let's move on to electron proton situation. So if you want to study actually electron proton, we should actually make sure that there are less number of energy levels so that we can understand it in better way. Okay? So let's say there are only two energy levels, n equals to 2, and oh sorry, there are two energy levels, so G equals to 2 and n are equals to 3. Particles are 3. So now these are electrons, so their spin is half, so we can actually arrange two particles in one energy level. So first situation which we can have is one electron here, one electron here, both, and third electron we can put either here or we can either put here. So how many number of ways there are? Two. Do you think there is any other way to arrange three particles in two energy levels? No. So number of ways are only two. What do you think? If this energy is 0, this is 1. Which of these state is a ground state? Left one or right one?
Left one, sir.
Left one. So this is a ground state because if you calculate the total energy, it will come out to be 1. If you calculate the total energy in this case, you will get 2. Why? The two particles are in 0 energy state. So energy is 0. One particle is in first 1 energy level. So means energy 1 electron volt. So total energy is 1 electron volt. In this situation, 2 electrons are in energy 1. So there are 2 electron volt energy. So this is your ground state. This is your first excited state. This is how you do the questions for electron or proton. Now let's say same question, two energy levels, but now let's make it spin 3 by 2. Spin 3 by 2. Particles are still 3. So now you can actually arrange 4 particles in one energy level. So now there are more number of situations. More number of situations. So either you can put these like this, like we had the before, but now there is one more option that we can actually put all 3 in one state only. Na? So these 2 extra are added. These 2 extra are added. So total number of ways become 4. Now you need to tell me what is the ground state out of these 4. There are 4 states in front of you. What is a ground state?
Third state.
4, 3 in first.
Third state is a ground state because the total energy is 0. This is ground. Now tell me what is first excited state?
First one.
First one. Excellent. This is first one. First excited. What is second excited? This is second, and this is third excited. So now I think hopefully you have covered. One thing which is left is, in this situation, the question was pretty easy and we were able to actually distribute the particles to see the results. But what if there are more number of levels and more number of particles? How we will actually do that? we need general formula like NCG we had in previous. The how we will have the general formula. So let's say I have a very simple, and this is not available in any book. Okay, I have actually seen it. I don't exactly remember where I have seen this. So if you have two energy levels and your spin is half, which means 2s plus 1 is 2. So split each energy level into 2. So what is the total number of levels you would have now? 4. Hmm? You have 4, na? Do you understand? If I split each energy levels into 2 levels, then what is the total number of levels it will become? 4.
Yes, sir.
So 4C3. If I do, then answer should be 4. Oh, just a second. Answer should be 2. 4. If I do 4C3, the answer should be 4. And in this situation, if I do check this, 4, 4, 8, 8C. No, okay. Okay. So I think I will give you the more general formula later. I am not exactly remembering that formula. That formula I will share with you later. Right now, understand that how the particles are distributed. And maybe tomorrow in the beginning, we can do that, how we actually have that general formula. I am not exactly remembering how many levels should be split it. We split the energy levels and then the formula can be generalized. So now coming to the third. Third is only thing which is left is, oh sorry, third. So bosons. So now there is bosons. Bosons are very cool particles because it was invented by Indians. So we are ground to earth people. So my teacher taught me like this. Sorry for that. So we are ground to earth people. So any number of particles can occupy ground state, first excited state, or second, because we are very adjusting people. Okay. So let's say there are 3 energy levels. Any energy levels you can imagine to understand the question, and there are 3 particles. So what are the number of ways you can? One idea is put one particle in all 3. Okay. Second idea is put 2 particles in one and one in here, 2 particles here, one here. Okay. Other is 2 particles here, one here, 2 particles here, one here. Okay. Now 2 particles here, one here, 2 particles here, one here. And then comes the last situation, all 3 in one, all 3 in one, all 3 in one. So what is the total number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So number of ways are 10. Okay. And the formula is n plus g plus 1 factorial, n factorial divided by g plus 1 factorial. So what is n plus g plus 1? 3 plus 3 plus 1 is 7. N is 3 and g plus 1 is 4. So if you do this, 7, 6, 5, okay, 7, 6, 5 and 3 into 2. Again, there is something wrong. Let me just check the formula very quick. N plus 3 plus 3, 6 plus 1, 7 factorial, 7, 6, 5. N is 3. And g plus 1 is 4 factorial. So 7, 6, 5 and 3 into 2. So answer which is actually coming is 35. So let me just check the formula very quick. The formula is okay. So by that time check that if I have arranged the particles in a correct way, it should either be only 10 na, or anything else. I have also taught it before. I don't remember why I'm getting this wrong. Okay, so the formula which actually is n plus g minus 1 and g minus 1. So this is what we are doing wrong. So now we'll do it. It is 5 factorial and it is 2 factorial. So now let's do it. 5 into 4 into 2. So it gives me 10. Understood? This is a formula, not plus, it was minus. Okay, if you put the answer, you will get the same answer. N is 3, G is 3, so 3 plus 3 6, minus 1 is 5 factorial, N is 3, so 3 factorial, and G minus 1 is 2, so you get the answer 10. Okay, so this is a formula which you should remember. So for fermions the formula is NCG, for bosons this is the formula. Okay, then comes the last, which is classical particles. Classical particles. But before coming to that, tell me what is a ground state out of all this? So this is your ground state. It has a 0 energy. And which state has a maximum energy? This state has a maximum energy. So now tell me, does any energy state is degenerate? If this is 0, this is 1, this is 2. So let's calculate energy for each. So this energy is 3, energy for this is 2, energy for this is 2, energy for this is 2 plus 2 4, energy for this is 2, energy for this is 1 plus 4 5, energy for this is 4, energy for this is 0, energy for this is 3, and energy for this is 6. So here you can see in the question they can also ask you what is the degeneracy of then system having an energy 2 electron volt. So what is that degeneracy? 2. Degeneracy is 2 because 3, because 3 states have an energy 2. 2 states have an energy 4, and similarly 2 states have an energy 3, and one state has energy 0 and 6. So sometimes in question I have also seen that in some good assignments what happen is if they ask what is the degeneracy of a system having energy 2 electron volts, students start to seeing this energy level, and they are actually detecting how to find degeneracy from here. No, if they are asking degeneracy of the state, it means you put the particles in it, then find the total energy of each state and then see how many of the states have the same energy. So 3 states have the same energy, 2 electron volt. Okay, that is also an important concept. Last particles are classical particles. Classical particles are actually distinguishable. So you will see actually the number of ways increases. Okay, in case of bosons, here you see. So I want to compare the classical case with bosons. Why? Because in bosons also you can occupy any energy, any number of particles in any number of states, and in classical particles also you can occupy. So what is actually the difference between them? So let's say there are 2 energy levels and there are 2 particles only. 2 particles only and there are 2 energy levels only. So this is an scene of boson and this is a scene of classical particles. Classical particles. Classical particles are sometimes also called Maxwell-Boltzmann particles because they follow Maxwell-Boltzmann distribution or classical distribution. So how do you distribute it in bosons? So first everyone use that formula and tell me what will be the number of ways in case of bosons. It's very simple. Just use this formula 3. So everyone agrees 3. Give a very quick answer. It's an easy calculation.
Yes.
Yes. So 2 plus 2 4 minus 1 is 3 factorial divided by 2 factorial into 1 factorial. So answer comes out to be 3. So what are those 3 ways? One is particle like this, one is particle like this, and one is particle like this. Very simple. Only 3 ways. Now comes to the classical situation. In classical, I said the particles are distinguishable. You can distinguish between two particles. So you cannot put dots. You have to put A, B. Okay. In this situation, it is like AA, AA, and AA because you can't distinguish. But in this classical case, it is AB. Now, BA is another state because this state and this state is different. Again, AB and BA. So you see number of ways increased by 1. Number of ways increased by 1. Why? Because the particles here are not, so particles here are distinguishable. You can distinguish between them. In this situation, AA is 1 only because if you put AA and then you change A here and change A here, both are same things, na? No difference at all. Okay. But in this situation, A is. So what is the general formula for classical? It is n raised to power g. No, sorry, g raised to power n. Okay, so 2 raised to power 2 gives you 4. So this is a general formula for classical particles. Now with the help of this knowledge, you can solve any problem, and I will always recommend you, especially if you are going for GATE exam, TIFR exam, or JAM exam. Even in GATE also these kind of questions comes along. In net these kind of questions are not very rare, not very common, but in all other 4 exams, I have seen that question repeats after every second year. This question is definitely in the question paper. So I will always recommend you. So please put this as a star mark that when you go to exam, please revise this lecture before that, because this kind of knowledge you forget. So if anybody have any question for today's lecture, then I will happy to answer that.